Welcome back. So, today is lecture number 11 and in this lecture we are going to consider synchronizing simulation and script file in MATLAB. So, in earlier lecture we have discussed basic MATLAB, how to generate, how to build Simulink blocks, then how to run Simulink model, then how to take data into MATLAB files. So, all these things we have developed, and in fact, at the end we have also considered the parallel RLC circuit and which is used to simulate a buck converter. In this course we want to go deeper into the Simulink model and we want to build conventional buck and boost converter and want to simulate, and also want to show instead of running through simulation we can run the Simulink model from .m file and we can create different test cases, we can create some design oriented test cases, and the simulation can be made faster by running through the .m file rather than going to the simulation file, Simulink file. So, the concept cover, the topic covers are like a model development of switch mode power converter. Here we are also going to consider discontinuous conduction mode. Then we want to discuss about Simulink model development of switch mode power converter with DCM enable blocks, then synchronizing Simulink and script file in MATLAB, and then interactive simulation case study. So, first we will take this block diagram which we have discussed in lecture number 4, and we have already built this circuit using block diagram and for a synchronous buck converter. So, here so this is our synchronous buck converter, sorry, it is not the synchronous one, it is the conventional one, and we have discussed that we can, this is the conventional buck converter because we have a diode here, and we have discussed earlier that this model we want to make a generic model which can be used for both synchronous buck converter as well as the conventional diode, diode based conventional buck converter, and we want to also show a comparative study when by considering a load step down transient, that what happen if we use a synchronous buck converter throughout and if we enable a diode conventional buck converter. Okay, so this model is well known, and this particular block we know that this particular signal is our switch node point, switch node voltage, and this block is designed for DCM enable operation, that means DCM logic, and if we take the complete circuit, then this particular block is responsible for switch node voltage, that means VSW or Vx, here it is shown switch node voltage. This particular block is designed for DCM logic. This particular block is used for output capacitor dynamics, and this block is designed for inductor current dynamics, Okay. So, now what we need, if we want to implement this particular converter, we need to select some parameter values, that means what are the parameters that we are going to consider. So, here we are talking about output inductance like output capacitance, this is related to our output filter, which consists of an output inductance and output capacitor. And here we have taken inductance value to be 1 micro Henry because we are trying to operate at 1 megahertz switching frequency, and this is our switching period TSW, and which is nothing but 1 microsecond, that means that corresponds to 1 megahertz switching frequency. So, these parameters are, we have to take this parameter from a data sheet, because here we have taken some values, but you can always pick up those value from data sheet specification, that what are the RDS on, and if you go to the data sheet of the inductor, then what is the DCR of the inductor. All these parameter we may not get the perfect value, but we can get an estimate about the parameters from the data sheet. Here we are using a set of data which you can change it, and this we are actually creating a .m file. Okay. Input voltage of 12 volt and output target voltage of 3.3 volt. Okay. So, now we are going to implement this block using MATLAB Simulink. First, let us go to MATLAB model. I mean, this is, we are now considering this MATLAB. Okay. So, first we have to create, we are planning to create, this is a file. Let us open a file, new file, script file. We can name it as a parameter buck converter, and this is a new file, and I am using the data, existing data from some other file. So, you can simply put this file. So, what I have kept here, all these parameters like inductance, capacitor, then time period, then RL, the DCR, diode resistance. Here I have kept diode drop to be 0, because if we, in fact we can make, we can keep it, but you can create a situation, if you use synchronous configuration, the diode drop can be ignored. If you use conventional configuration, then we can add diode drop. So, we can use either of these, but here I have taken diode drop to be 0, but you can incorporate it. Okay. So, input voltage is 12 volt and output voltage, reference voltage is 3.3, and this is taken as, if we want to take a Sawtooth voltage that we discussed, we took an upper value and the lower value. The lower value is the base value, which we kept as 0, and upper value is 10 volt. Although in this presentation I am not going to use this, I am going to use a fixed time period for simulation. Then what we will do? Okay, let us now, we want to create a Simulink model, that means this is our parameter file. Then we need to, I need to open a new file, a Simulink model. So, in this Simulink model, we know how to develop these blocks. That means, let us start with a basic commonly used block. What basic blocks we need? We need some constant, then we need integrator, then we need summation switch block, then we need scope if you want to simulate, then we need relational operator if required. At this point we may not require, then we need summing block, so on, and then we need also a constant, because a gain, because these are the thing we are going to consider in this building of Simulink block. So, first we want to realize the current dynamics. What is there in the current dynamics? If you refer to our presentation, if we refer to this model going back, the current dynamics here, this particular block we are talking about, this block. In this block, what is there in the current dynamics? That means, first inductor voltage, we have to generate inductor voltage. Inductor voltage if we do not consider the discontinuous conduction mode, then what is the inductor voltage here? The inductor voltage is nothing but this side is the switch node voltage minus the drop across this resistance. That means this is my switch node voltage, this is the drop across this here, and then this terminal is the output voltage, this terminal output voltage. So, that means VL is equal to Vx minus RL IL minus V0, that is by L, sorry, that is my VL. Okay. So, let us start our block diagram. Okay. So, we want to first create a VL block. What is VL? That means after VL what is there? We know that L DIL dt is equal to VL. So, L DIL dt equal to VL by L. So, here we should use 1 by L. This thing we already did it earlier. So, it is 1 by L. This is my inductor value. So, this part we can insert some text. So, this part, then this is our VL. What is there in the VL? Okay, let us consider the VL. It consists of Vx minus, that means minus plus minus. Okay. Again we need to have a gain, and this gain is R underscore L, that is my DCR, and this is connected here. It is because this integrator output is my inductor current initial value. Okay. And we can set the initial value I L 0, that is my initial value, and we have to define this initial value in the script file, otherwise the symbol will not be executed. We have to give some, assign some value. Okay. So, we can connect this block. Okay. Next we need Vx. What is Vx? So, I think what we need another block is that, yeah, we have some constant here. So, this constant, let us say we define as a Vx. Later on we will replace what is Vx. So, this Vx is added here, that is my switch node voltage, and then what else we need to consider is that output voltage, that means I need another is the output voltage. This will create my the dynamics of the inductor current, that means inductor current dynamics consist of these parts. Now, this is my V0 output voltage. So, this will give me the inductor current dynamics, but as I said this is VL, but the VL in general when there is no discontinuous conduction mode, this will be this one, but if we incorporate discontinuous conduction mode, the VL will be 0 when DCM point is detected, 0 current is detected and you have a diode. So, in that case we need to incorporate a switch. Okay. So, let us take it back. Instead of directly connecting to this, we need to connect through a path. What is that? This is my path. Now, this block switch, if what is the logic of this switch? We will put a threshold of 0.5. Okay. So, that means if the middle one, that means which is my control signal, if it is greater than 0.5, it will take first channel, the first input, the output will connect to the first input. If it is less than 0.5, it will take the second input. So, our case it is the second input, because we are going to generate a control signal which will be 1 when the DCM is enabled and the DCM is detected. Okay. So, that means this is my signal, and for which we need to put 0. That means, when the DCM is detected, then we will set to 0, inductor current dynamics, and then we need another signal here, which is my QD. That means, my 0 current detection logic. So, in this what we need? This block, this particular block, these are my different requirement of the input, this is just a constant. So, if you take it for this inductor current dynamics realization, this QD, that means this is my what? QD, Q underscore D. This logic is my discontinuous, this is a logic signal which will be either 1 or 0. If it is 1, it will take the VL will become 0. If it is 0, then VL will take VL, that means inductance voltage will be equal to Vx minus ILRL minus V0, that we have already realized. Okay. So, now we want to create subsystem. Okay. So, want to create subsystem. So, this is a scope and that we have already discussed. So, in this subsystem, this is the block, what everything will be inside the block. So, we want to create a subsystem, we create a right click, create a subsystem. Now, it creates a subsystem. If we go inside, we will go inside the subsystem. So, this subsystem is for current dynamics. So, for it is like inductor dynamics. Okay. So, it is corresponds to inductor dynamics. What is the input? The first input we need, this is my switch node voltage Vx. What is the second input? This is my output voltage. What is the third input? This is my QD. And what is the output that I want? Here is my IL, that is my inductor current. So, this is consistent that we have connected Vx to Vx, V0 to V0, QD to QD, but neither V0 is available, not QD is available, nor Vx is available. So, you can't generate inductor. So, we will keep this block by inductor dynamics. So, we need to generate these blocks also. So, this is the first block we have generated is a current dynamics, even we do not need to connect scope at this point of time. Now, since we have already created a subsystem, we can create another subsystem for voltage dynamics. So, this is for capacitor dynamics. So, capacitor dynamics, that means what is there for this? What are the input to the capacitor dynamics? If you go and see, this is my capacitor dynamics. If you go to the previous slide, okay, so previous slide, okay. So, this is my capacitor dynamics. That means, what is the input to the capacitor dynamics? Is the inductor current, and all other elements are, and another input is the load current. This is my load current, one input, the other input is the inductor current, and output is capacitor voltage and output voltage. So, you can keep capacitor voltage and output voltage. Okay. So, with this, let us go to the Simulink block. Here we will write Vc, it is the capacitor voltage Vc0, and this should be 1 by C. Here we do not need any switch, it is simply what we need? We need inductor current minus load current. Okay. So, we need inductor current minus load current, that is my capacitor current. If I take this after the summing block, okay. So, this will be what? This should be my inductor current, Oh, actually there it is repeating. So, here we are talking about Vc, V cap, capacitor voltage, and here we can take I L. Okay. So, this is my inductor current dynamics. Then I can use load current here, like a here load current, or I can use I out, output current. If you subtract, this will become my capacitor current, and this is my capacitor voltage. And then what is the output voltage? It is the capacitor voltage plus the drop across the ESR, which is RC into IC. That means I need to use this block, and this block is my RC. The symbol must be consistent, otherwise it will give error. Okay. So, now we are ready. This is my output voltage, and what else we have to add? We have to add the capacitor voltage, and that will give rise to my output voltage, that is my V 0. V 0, yes. So, I do not need. So, this is my output current, output voltage dynamics. That means the capacitor dynamics, I got it. It consists of, it require input as an inductor current and output current, and then capacitor voltage and output voltage. And you will see for our resistive load, the output current is nothing but output voltage by resistance. So, you can add a scaling factor outside. So, that I will discuss. Okay. Now, what else we require? The next block is require the switch node voltage. That means Vx is not known. So, we need switch node voltage. Okay. So, switch node voltage, switch node voltage. So, okay, switch node voltage. What is the input to the switch node voltage? Switch node voltage, if you go to the circuit, what you will find, the switch node voltage is, I am talking about this particular part. So, it consists of input voltage minus, when the switch is on, this is input voltage minus the on resistance of the high side switch into IL, the current. When the switch is off, it is minus of Vd, Id, Rd into IL, that means the diode drop into RL, that is it. Okay? Just switch node voltage. So, we can go for switch node voltage. So, what is the input? Input we require, so output is we are talking about. Okay, so this is, let us say, so output is Vx. We are going to use the switch node voltage. Vx is my output. We do not need any dynamics here. Switch node voltage. What is switch node voltage? That is equal to V in minus, sorry, yeah, fine. So, just a minute, we will disconnect all this path. So, first let us figure out what is the switch node voltage. So, here we are taking inductor current as the input, sorry, it is the input voltage, inductor current, let us not connect. Okay. So, we need first is that input voltage, V in, input voltage. So, we need input voltage Yeah, we need input voltage. V. So, V in should be connected here. Then what is there? I want IL into R1. IL into R1 is my another one. Okay. And next one, this is my first one. In fact, I can use like this. Okay. The other one that I can take, yeah. So, here it is minus Vd. Okay. So, I do not need, this is my Rd, the diode resistance multiplied by inductor current, and this diode drop all are negative. So, constant is my diode drop. So, this is simply V underscore D. And then we have to connect a switch. So, it will take the first input when the switch is on, otherwise it will take the second input when the switch is off, and this Q is my gate signal. That is it, and that is my Vx. So, we have generated Vx. When the Q is 1, it will take the first input, when the Q is 0, it will take the second input. So, we have developed this Vx. Next part what is left is that DCM enable block. The next part is required is that DCM enable block. What is the requirement here? We need to sense inductor current, and also as I discussed, inductor current is there. We also need to, I can remove all this stuff here, because this I just copied pasted from the previous block. So, we do not need input voltage here, we just need inductor current. Yeah, all we can keep this side, no required. What we need to do? First, inductor current should be compared with the 0 current. That means, we need a logical block, comparator, relational operator. Now, we have to check whether inductor current is less than 0 or not. So, this is the first input, and what we need to compare with 0. This is my 0. Okay. So, if the inductor current goes below 0, then this output will be high. Now, we need logic block, that means logic and logic, and we need 3 input AND. What are these? What are the first input? We have discussed this 0 detection circuit output is one of the input to the AND gate. Then what is the other input? The inverted logic of the switching signal. That means, we can create another NOT gate, smaller size NOT gate. This block we have, and we need to give a DCM enable logic, which is our, you can say DCM enable logic, which can be set to either 0 or 1 logic, and the output is my QD here. This is my Q underscore T. That's it. We are more or less done. Now we are ready to go for the next. So now we have DCM enable block, we have switch node block, inductor dynamics, all these blocks are there. Okay. Now we want to slowly connect different. So that means this Vx should be connected here, the switch node point. So we need to bring a little bit down. Okay. Then output voltage should be connected here. Okay. Then QD should be connected here, zero current detection. I out, that means we need to consider a gain block here, which is 1 by R. That is my load resistance, but I can use, I will show you, I can use constant current load also, combination, there is no problem. I out. Okay. Then for DCM enable, I need to consider a constant which can be, you can set to 1, then the DCL will be enabled. If it is set to 0, it will be disabled. I need to use a proper gate signal, so that is my input is required, and I need to connect through the inductor output. Then inductor current is also required here. Okay. Now I need to consider input voltage. Here also I need inductor. Then input voltage is my V in. All right. Then I need to consider a source, and here I am taking a pulse width source. The pulse width source amplitude is 1, time period is T, and let us use a 50% duty ratio, and that I am using for for my converter. Yeah. So I am using a pulse here for my switching. Right now I am using a fixed frequency pulse, the same is connected here, 50% duty ratio, and I want to see various output, like so I need to check 3 axes. So one will be my inductor current, the other will be my output voltage, and the third one is my gate signal, which is connected here. Now we are ready, and we need to give a name here. So is a buck converter. That's it. Then what else? Let us go to the simulation file. We have defined all these parameter. We have to run this parameter file first. Then the values are loaded here. Then let us try to run it. So we will run for 2 milliseconds and see what happens. So some of the gains are not defined, like R, VCO, initial conditions are not defined. So we need to define those parameters as well. That means IL0. What are the symbol that you have used here for current dynamics? IL0. So that we need to set here IL0, and then other parameters for the capacitor voltage is this. So that also we need to define. Okay. So now R, let us say some resistance, load resistance of R equal to 1 ohm. We run it again, and then we want to run the buck converter and see what happens. So, this is the simulation of the buck converter, where 12 volt was my input and 0.5 was the duty ratio. Okay, so, let us see what are the simulation results. So, this is my inductor current, this is my output voltage, and this is my gate signal. So, if I want to give some property of this one, so I want to show you that when the switch is on, you see when the switch is on, then the current is rising, and when the switch is off, current is falling, and the output voltage profile looks quite similar to the inductor current profile. And we discuss, if we set ESR to be 0, for example, we set ESR to be 0, then we will get ideal capacitor, and then if we run the simulation, we will see what is happening. Now, if we want to see how does the voltage profile look like, they are not exactly same as, yeah, it is just rising. So, it has not reached steady state. So, if we take few cycles here, then if we try to see the voltage output, still there are some, we have kept ESR to be 0, but it is still showing the profile, although very small, maybe it is a numerical error. So, we need to set the simulation configuration parameter if you want to improve the accuracy of the simulation, and let us see what is the simulation. Yeah, so maximum step size we should not take any arbitrarily. So, let us set, we set at least very low value, and here you can see trapezoidal method. Relative tolerance also need to improve, because that is quite large. So, I generally prefer to use like a 12. Now, if you run the simulation, maybe the simulation will be slightly slower, but that is okay. Okay. So, now if we want to see the voltage profile, its look perfect capacitor voltage that we have discussed. That means, whenever the average inductor current reaches its average value, from that point capacitor start charging. Whenever it again falls below the average value, then capacitor voltage starts falling. So, that is very consistent, because the capacitor current is positive when inductor current is above the average value, which is the load current for this case, and below it is below the load current. So, with this we can also implement. Now, we implemented buck converter, and next I want to we can take the boost converter example, we can buck converter, we can do simulation, we can also implement boost converter. So, I will in the next lecture I will show different boost as well as buck converter simulation example, and just the final touch, like in this case I want to show that this simulating model that we have developed, that means these are the various inputs. If we take them little bit away from them, and we want to further create a subsystem, that means if we do not okay. So, we want to create a subsystem of this block. So, it is possible that you create a subsystem. So, in this subsystem it is a buck converter. Complete buck converter. What are there in the subsystem? The first one is Vin. The second one is gate signal, that means I can say gate signal. The first one is my input voltage. The third one is my DCM logic, DCM enable. This one is my output voltage. Now, this is my inductor current, and this is my capacitor voltage, and if I want to see output voltage, yeah, it is already there. So this is my output voltage and this is my load current. Okay, because load current is an input here. So now I can create. I am going to use this model in the next lecture. So we also have a boost converter as well. So you can connect between output voltage and input voltage, this enable logic, and we can continue to simulate, like whatever we did. This is the output voltage and this is the what do you say, the gate pulse, and you can again run the simulation and the same thing, but this subsystem will make the whole converter is a single block, and we can, if you want to connect multiple converter in cascade, so you will just drag and drop those blocks and you can connect it. So that means we have discussed about MATLAB Simulink model development, and I think this presentation we want to limit our discussion to this point. So we have developed Simulink model with DCM activation logic, deactivation feature, and interactive case study with MATLAB study. We have demonstrated simulation case study, but interactive case study using script file and the Simulink file, that will be shown in the next lecture. And we have developed buck converter model, and now the similar approach can be used to generate boost converter model. So that is the end of today present lecture. Thank you very much.